Okay, so thank you everybody and welcome to the fourth talk of the FDHA Lab, the Full Displacement Hazard Laboratory within the Fall to SHA group. And today we're happy to have Alessandro Valentini speaking to us. So Alessandro, I would say, is an expert in both seismic and fall displacement hazard assessment. He got his PhD at Chieti Pescara University in 2019. Then he worked as a consultant at IAA in Vienna. He is now working at INGV, which is the Italian National Institute of Geophysics and Volcanology, and is also a senior guest researcher at University in Vienna. Today we'll speak about the comparison among different PFDHA models, which I personally believe is a really needed discussion we need to have within the community. So, well, Alessandro, the floor is yours. You know, you have about 45 minutes or so, whatever you want, and then we have some room for a Q&A session.
Okay, can you? I cannot share the screen. Can you give me the permission?
Okay, let me check impostazioni. Okay, you now should be able to do it.
Yeah, thank you. Thank you very much for this kind introduction, and thank you for the invitation. And yes, as you said, I will give you this talk today about a comparison among different PFDHA models. And can you see the PowerPoint full screen?
Yes.
Okay. Okay. Very good. And okay, as I said, the topic of the talk will be the comparison among different PFDHA models, and the results of this comparison is part of an IAA project started in 2020, 4 years ago. And briefly, the content of the talk will be just 5 minutes. I will give you some introduction and motivation of the project. And the project is made by three steps. Step 1, 2, and 3. Step 3 is basically the drafting of the technical documents. So I won't show anything about the documents. I will show you briefly the first step, and then more details about the second step of this project. Then we will have time for maybe for some discussion. As I said, this is a project led by the International Atomic Energy Agency.
Excuse me, Alessandro.
Yes.
Are you able to? Yes, thank you.
Okay. And the project led by the International Atomic Energy Agency. And I don't know if you are familiar with the IAA documents, but basically there is this hierarchical structure of the documents. On the top, there are safety fundamentals, then there are safety requirements, safety guide. And then below there are maybe thousands of technical documents that help member states to address the requirements and the guide in the main important IAA document. In particular, the safety fundamental, safety principle number 8 of the safety fundamental say that all practical efforts must be made to prevent and mitigate nuclear or radiation accidents, and the effects of external events at a particular site must be evaluated in order to apply this principle. And for external events, the principle means earthquake, tsunami, flooding, everything that can damage the nuclear installation. In particular, the safety requirements number 1 provide requirements on evaluation of fault capability and the ground motion hazard. And in particular, for capable fault, it says that if a capable fault has the potential to affect the safety, an alternative site shall be considered. In addition, the safety guide number 9 provides guidance on seismic hazard assessment and fault displacement hazard assessment. And in particular, say for that PFDHA is recommended to evaluate fault displacement hazard for existing nuclear installation if a capable fault is discovered and cannot be avoided. Looking at the detail of SSG9, as I said, SSG9 recommend to evaluate fault displacement hazard when there is a capable fault. And just give us some example that a member state can face during the nuclear installation process, let's say. So there are two cases where the site is a new site, or where there is or the site is an existing one. And there are cases where the capable fault is within the site area or within the site vicinity. We are talking about 5 kilometers, or outside the site vicinity. So depending on the combination of these two cases, the presence of the capable fault is an exclusionary criteria, or it's a discretion of the regulatory body, could be, or in some cases when the site is already installed and the fault is discovered years after, PFDHA, so fault displacement hazard is needed, and the PFDHA, probabilistic fault displacement hazard, is recommended. In addition, the revision of SSG9 published a couple of years ago also make a distinction between primary and secondary fault. And in particular, it say that the primary fault rupture is in the vicinity area, so within the 5 kilometers radius, and the secondary fault ruptures are within the site area. This is an exclusionary criteria if the primary and secondary fault rupture effects cannot be compensated for by proper design or engineering measures. So basically say, if you find a secondary fault in the site area or primary fault in the site vicinity, you can still continue with the building of a nuclear installation, but you have to prove that a displacement on that fault, it's not an issue for the nuclear installation. And then if the primary fault is outside the site vicinity and the secondary fault are within the site vicinity, but outside the site area, this is a discretionary criterion, and then depend of any member states can decide whatever they want. So having said that, and also given the fact that PFDHA is quite new practice, let's say maybe PFDHA was born maybe 25 years ago, but start to be a practice in the last maybe 10 years or less. So for this reason, the IAEA member states wish to have more practical guidance on PFDHA, and this means that they want technical documents to address this topic. And in response to this, the external event safety section, it's one of the maybe hundreds of sections within the IAEA, has been conducting efforts to prepare two tech docs on this topic. One is already published, and if you Google IAEA Tech Doc 1987, you can easily download it. And this document is talk about the state of art and practice at some nuclear installation. There are three examples: Double Canyon, and another nuclear installation in Yucca Mountain in US, and another one in Slovenia, Krško nuclear power plant. And but the talk of today is more focusing on the second tech doc that is still in progress. We are working on that. We have a very good draft, and we hope to publish the document in the first half of the next year. And this is the title of the tech doc: Benchmarking Current Practice in PFDHA for Nuclear Installation. And today I will show you some preliminary results about this project. As I said, the project is made by 3 steps. The first step started in 2020 and with a kickoff meeting, and also the project started the same days. And then the main goal of the step 1 was to engage with the originator of the published PFDHA models, published up to 2020. So we were able to contact Bob Youngs, Rui Chen, Rob Moss, Tadashi Anaka, and Francesco Vicini, and we provided them input data for a fictional scenario, and we asked them to run their model. They ran Youngs et al., Petersen et al., Moss and Ross, Takao et al., and Nurminen models. So they start with their calculation with the same input, basically mean the same source characterization and the same seismic occurrence rate. I've been the project manager of this project, and the former technical officer was Yoshi Fukushima. Now he's retired, and the new technical officer is Zelep Gulers. And also we made an advisory team made by Steve Thompson, Toshi Sakai, and Emanuele Vialle. We had the first meeting with the model owners in January of the 2021, and the results of the step 1 are published on BSSA. Also, you can find the paper online, but maybe it's not an open journal, open journal. If you have any trouble to download the paper, you can also email me and I can share with you. And briefly, I will show you the main results of the step 1. The scenario that we created was based on Kumamoto area, an area affected by the 2016 earthquake in Japan. And we provided the input information for 2 exercises for principal faulting and 3 exercises for secondary faulting or distributed faulting. These are the results for only one principal faulting exercise, where the source was the whole Futagawa fault system, and the magnitude range between 6.5 and 7.2, and all models were in a good agreement. But for distributed Raptor exercise, where the site was 5 kilometers away from the principal fault, you can see that the big variation among the models. And so some take-home messages from this step 1, but with a focus on secondary faulting ruptures, because this is most critical for nuclear installation. Because if you find a primary fault below your nuclear installation in the site area, maybe 99% of the time is an exclusionary criteria. When you have distributed ruptures, it's always up to the regulatory body. So the whole project it's taught for both both things, for principal and secondary, but sometimes we put our efforts more on the distributed rupture exercise. And so as you have seen, there are huge difference between the models. And also we compared all models. The models that we compared are built with a different database, and also are taught for a different region, and so are for different kinematic and tectonic environment. And so maybe the main message was that a given model must not be applied blindly. So you have to pay attention of the geology, of the kinematics of your structure, and also of the source characterization, and so on. Otherwise, the difference that you can obtain are very, very, very different, and also very, very large error. So we started the second step in July of 2021, and the goal of the second step was to implement all models already published, and also the new one, for 3 scenario sites, not only one. And we invited basically all participants in the Fault Displacement Hazard Initiative. And today we can compare the hazard curve for the old model and also with the new one. They are listed here. there are model of Chiu et al., Lavrentiadis and Abramson, Vicini et al. 2024, and the Kuhn et al. 2024. Lavrentiadis and Abramson is published. Vicini, Kuhn, and Chiu are under review on earthquake spectra. We also invited the other experts, mainly from consultancy, from practitioners like Letis, Rizzo, Sester, Fugro, because they have their own code based on, for example, based on Youngs et al., but it's not the code made by Bob Youngs, but made, for example, by Fugro or Sester. And so we invited them just to have also an indication of the let's say, verification and validation of the models. And it was very useful exercise, this. We had a third and then fourth meeting with the model owners in June 2022 and June 2023. And basically, we concluded the second step last year, and the results of the second step are under review on earthquake spectra. As I said, the third step is the documentation of everything that we have done in the last 4 years in IAEA TechDoc. But the talk will focus only on the results on the paper under review on earthquake spectra. So briefly, I will also introduce the 3 case study. The one is here in south of Japan, and it's a strike slip faulting case study in the area affected by 2016 7.6 magnitude 7.6, if I remember well, Kumamoto earthquake. The second exercise is based on the area affected by 2019 Leteli earthquake, is a reverse faulting earthquake. And both are requests of the member states. And the third one was added after the technical meeting in November 2021. And there is, maybe you know very well, North earthquake in central Italy, normal faulting earthquake. Yes. In the second step, we could compare 5 models for the strike slip environment, 4 for the normal faulting, and 5 for the reverse faulting environment. And these allow us to do a more meaningful comparison than step 1, because we could split the comparison only among the models for strike slip, for reverse, and for normal. As I said, we also did a little exercise on hazard code and verification. And we prepare the input parameters and to be shared with the model owners for 1 principal faulting exercise and for 3 distributed exercise. We did this just in order to explore uncertainties in the moment magnitude, in the moment rate, in the slip rate, in deep direction, and so on. At the end, we could compare 5, 4, and 3 different models for principal faulting exercise, respectively for Kumamoto, Letei, and Noccia, and at least 2 different models for each kinematics. So it's not too much, but it's better than nothing compared with the step 1. We could compare only 4 or 5 models for only 1 kinematic environment. Everything is discussed in the tech doc, and today I will show you only the results for the principal faulting displacement for 1 distributed case, because these are discussed in the earthquake paper. So in the next 3 slides, I will show you I will give you some information about the 3 cases. Just some information about the fault geometry and the geometrical parameters and kinematic parameters of the fault. So this is the Kumamoto strike slip case study. We are here in the south of Japan. The 2016 earthquake ruptured the Futagawa fault, the first segment, and the part of the Inago fault system. And the distributed rupture are located mainly in this area here. For the full exercise, we put the site for the principal exercise here, where is the yellow star, and for the distributed cases, we put the site here and here. I will show you only the results when the site for distributed rupturing is here, and it is 5.2 kilometers far from the principal fault. You can read the number on the tables. The magnitude range go from 6.5 to 7.2, and yeah, for the principal fault exercise, we consider only the UTO segment, so the moment magnitude will be 6.5, and the distance for the distributed case will be 5.2. This is the Norcia normal case study. You know very well the area, maybe better than me. The site is here for the distributed exercise. It's 7.6 kilometers far from the Monte Vettore fault. The site is here because here we have the evidence of distributed rupturing in a tunnel, documented in a Galli 2019 paper. I don't remember the amount of displacement, maybe around 10 centimeters. And the moment magnitude for the Monte Vettore fault is 6.7, and again, the distance for the distributed case is 7.6. And then the reverse case study. This has been the most tricky exercise because we are in a very shallow environment, very low magnitude, as you know, 5.9 magnitude. The deep of the epicenter was around 3 kilometers, and there are evidence of surface rupture for very low magnitude. And also we are in a low seismicity area, and this means that the source characterization is not straightforward. I will show you some slide after. The huge epistemic uncertainties that this when you are in low seismicity area, when you cannot characterize very well the seismic source, the very huge epistemic uncertainties that you can get. Okay, I think I've said everything about the three cases, and yeah, just some warning before to show you the results. I will show in the next slide the comparison for the three cases, but you have to take in mind that the models that I'm going to show you, the data curve of the models are made with a different database, and also sometimes the database allows the modelers to build the regression, the empirical regression for a different slip component. So as you can read from the table, some model can predict the vertical component of the slip, some the lateral, some the net. So when we are comparing the different PFDHA models, also the comparison is not straightforward because you have to take care of the slip component. It's different among the models, and also the classification that the models made about the principal and the distributed rupture. For the old one from Youngs, Petersen, Takao, and Moss, sometimes you can find empirical regression for principal and empirical regression for distributed. But for the new one, sometimes you can find for Lavrentiadis, Q, and HU, you can find only the empirical regression for principal faulting rupturing, but it's different the classification that they make about the principal faulting. Sometimes it's a sum of one or two principal faulting if there is an overlap, for example, or sometimes you don't find it's an aggregate measure of the displacement. And so also for this reason, again, the comparison it's not, let's say it's not apple to apple, but it's also not apple to orange. So it's, let's say it's still apple to apple, but with some warning to take care about. So let's start to see the difference, the comparison of the PFDHA model. Let's start with the Kumamoto, and let's start with the principal displacement hazard curve. Here we have annual frequency of the exceedance in y-axis and the principal displacement in the x-axis. What we can say about the comparison? Okay, before to say something, the comparison is among Takao model, Petersen, Chu, Lavrentiadis, and Ku et al. So basically, we can say that the hazard curve are generally in good agreement. The difference in y-axis are mainly given by surface rupture probability models adopted by different analysts. And I can say this because the occurrence rate of the fault is the same for for all models, because it's an input that has been provided by us. And so the starting point of the curve are mainly given by these two things: the seismic rate of occurrence and the surface rate probability. And why? Okay. So, and I'll show you the difference among the surface rupture probability models adopted by different analysts. For example, Kuhn et al. Model assume a probability equal 1. Petersen, Chu et al. Used the Westlake Coppersmith 94 for all kinematics, and for a magnitude 6.5, this probability is around 0.7, 70%. Lavrentiadis et al. Use a case-specific surface rupture probability by plotting the rupture plane over the deep slip surface. It's not plotted in this graph. And Takao et al. Use Takao et al. 2013 model, and for a magnitude 6.5, this probability is around 0.45. In addition, the Takao model further scaled down with a factor of 0.45 to consider the probability of primary rupture at site. It's the so-called the P2P factor. And so you can see here the difference of these surface rupture probability models. The Takao model is the lowest hazard curve, mainly for this reason. The other one are in a good agreement also because the surface rupture probability models range from 0.7 and 1. In addition, there are a significant difference for specifically for longer return periods, and this can be explained by dilatory variability in models and the truncation of the standard deviation in the fold displacement model. So when we talk of PFDHA, probably you already know, but it's just a reminder. We have one part of the equation that is given by the occurrence rate of the source, the activity rate, and then we have one part for the principal faulting, and then one part of the equation is for distributed faulting. And in both cases, we can split this part in other two parts. One we can call surface rupture probability model. Let's call it this way, and the other one is the fold displacement model. That basically are the function that show how the displacement show the amplitude of the displacement, how decrease with the distance, with the increasing of the distance from the principal fault, or how the displacement attenuate along the strike of the principal fault. And so we can say that this part, the fold displacement model, has a control on the hazard curve, mainly in the x-axis, and this shift the hazard curve from left to right in the x-axis. As I written here, also the new prediction models did not implement log normal distribution, but they implement a different distribution, such as power normal or Box-Cox transformation. And so the explanation of the difference for long return period in the displacement value mainly are given by this aspect. Here in this plot, I show you what happens if we remove surface rupture probability contribute. This allows us to do a more direct comparison, and I show you this only for the Kumamoto exercise because this is in progress. We got three review during the review process, and we are working on the review of the paper. And one comment of the three reviewer asked us to do a comparison in this way, removing the contribution of the surface rupture probability, and in order to see the real difference among the model. And you can see they start from the same point here because the currents rate are the same for this exercise, and then you can see that the difference start to be much important here. Let's say for annual frequencies of exceedance higher than 10⁻⁵. Okay, this is the NORCHA case study. We could compare only three models: Lavrentiadis, Young's, and Cohen. Again, they are in a good agreement. The difference, the y-axis again, are given by the surface rupture probability. Cohen again used a PSR equal 1. Young's et al. Implemented the model with PSR using Bayesian and range data set, and this yield a probability close to 1 for a magnitude 6.7. And again, Lavrentiadis model is a case-specific surface rupture probability model, but it's close to 1 also this probability. And so you can see the difference range from 1, 0.9, and there are no big difference in the hazard curve, at least in the first part of the curve. So higher is the magnitude, lower are the difference in the surface probability rupture, as I shown you, and so lower is the impact on hazard curve. Again, the difference for higher value of displacement are mainly technically, let's say, depending of the technical choice of each model. And yeah, that's all for the NORCHA case. So now let's see the Leté reverse case study. Now the hazard curve are not in a good agreement. You see a big discrepancy between Takao and Q Lavrentiadis model. In the middle, there is Moss and Ross model, and they range from an halfway of 10⁻⁴ to 10⁻⁷, so a very huge range. And the difference in the y-axis, again, if it is not clear, are given by the surface rupture probability models. And Q et al. Apply again a PSR equal 1, Lavrentiadis and Abramson model, the same case-specific surface rupture probability. Moss and Ross apply the Moss and Ross 2013 regression for reverse kinematic, and the probability is around 0.1 for a magnitude 5.5. And Takao, also considering it's lower than 1% the probability of having a surface rupture for a magnitude of 5.5, and in addition, this probability is scaled down again for the P2 factor. And so you can see the difference from Q et al. Model where the PSR is equal 1 and Takao, it's less than 1%. It's very produce a very big difference in the hazard curve. And so we say now that lower is the magnitude, higher are the difference in the PSR, so higher is the impact on hazard curve. And we can say this because we have only this model for a reverse environment. And so if a practitioner, if a consultant apply tomorrow this regression, this empirical regression for a site in a reverse, let's say also in a low seismicity area in a reverse environment, you have to keep in mind this. So there could be a huge difference among the models available nowadays. But as I already said in the introduction of the 3 exercise, the tail earthquake is a very shallow earthquake with a 4-kilometer seismogenic tap. And so the applicability of the empirical probability of surface rupture model may be controversial for cases like this. And this need that the community, PFDHA community, need different approach for a cases like this. And maybe not only empirical approach, but also we need a simulation, numerical, analytical, you can say, I don't know, you can say in a different way, but we need the simulation approaches as well. And so another warning, big warning, and maybe this could be the main conclusion for principal faulting case studies. We have to use correct model and valid assumption to avoid very, very large errors. Okay, now let's move on distributed displacement hazard curves. Let's start with the Kumamoto exercise. We could compare only 2 models, Takao model and Petersen et al. Model. As expected, the distributed rupture displacement hazard curve are significantly low when compared to the principal fault displacement hazard curve. If you remember, in the Kumamoto case, the principal faulting were around 10⁻⁴ in terms of annual frequencies of exceedance. Here we are around 10 to -5. Okay, the site is 5 kilometers far from the principal fault, so also this is important. The difference in the y-axis now are given by the distributed surface rupture probability models adopted by different analysts. So are different from the other probability models, the surface rupture probability models, because now this probability give us an idea of the probability of distributed surface rupture with the increase of the distance from the principal fault. And we can see here the difference among Petersen and Takao for the Kumamoto case. We are in the more or less in order of the difference is one order of magnitude of let's say a factor of 10 of the difference, sorry. And this is translated in the hazard curve. You can see also here a factor of 10 of difference in the hazard curve. The difference in the x-axis depends on the different fault displacement model adopted by different analyses. So also in the distributed displacement exercise, we have the 2 components, one for that impact the y-axis, that is the probability of surface rupture, distributed surface rupture, and the other one is the fault displacement model that give us an idea of the attenuation of the displacement far from the principal fault. For higher return periods, slope of the hazard curve are dominated by the displacement prediction model and the associated aleatory variability model. The probability of exceeding distributed faulting displacement scale the hazard curve to the right, as happened in the principal faulting case. Because the hazard curve is flat for displacement less than the median displacement. In this case, the 2 models intersect more or less at 40 centimeters. And this means that the two models have a quite different median estimation. Oh, let's move to NORCHA distributed exercise. The set to fault distance is 7.6 kilometers. And the comparison is between Vicini and the Young's model. We have the same consideration that I did for Kumamoto. For halfway equal to 10⁻⁷, that start to be, maybe it's the lower threshold for nuclear installation The estimation is around 30 centimeter for Vicini and 50 centimeter for Young's model. And for the difference in the y-axis, again, the difference given by the distributed surface rupture probability model, and you can see here the difference between Young's and Vicini. Okay, I told you the difference for this alpha. And then the last case, the Leteille, a reverse case study. The difference here, we are less than 1 kilometer far from the principal fault, and the difference in the probability in the distributed surface rupture probability models, it's not too much, and so you can see the impact on the hazard curve. They are almost pretty close, at least for the starting point. But for this case, again, the magnitude is very low, 5.5. The hazard curve are very, very low, maybe 10 centimeter for alpha higher than 10 to minus 9. So very, very, maybe 1 billion of years. I don't know, maybe it's older than the age of the Earth. So, but this is also, it's interesting to see this for low seismicity area. So some conclusion for the distributed rupture case study. And also, again, some warning, because some model extrapolate the probability of distributed surface rupture for distance higher than 3 kilometers. And if you remember, the site vicinity for a nuclear installation is around 5 kilometers, but some model could extrapolate this value for higher distance. And for example, Petersen and also Vicini model extrapolate this probability of distributed surface rupture for distance higher than 2 kilometers. So this is a warning when we are in the distance 4, 5, 6 kilometers. So we have to know that we are applying an extrapolation of an empirical regression. Some models are not suitable for all site dimension. For example, the Young's model, this curve are obtained with a grid 500 per 500 meters. So it's challenging to apply when the site is smaller or is larger. The new model, for example, Petersen and Takao have this regression for a different cell size from 25 meters up to 50 meters. And a better quality of the geological input data reduce epistemic uncertainties. This is not part of the paper in publication, but this will be part of the tech doc, because as you can see, we go from low seismicity area and the high seismicity area. In the Kumamoto case, we could provide a very good input information for the source characterization, and this all of a very a not big epistemic uncertainty in the source, only in the source characterization. But when we are in the low seismicity area, the fault are very poor constraint. We don't know anything about the fault length, the seismogenic thickness. Also, for example, in Leteille, we have uncertainties in the deep direction of the fault. So, and when we don't have a very good source characterization, the epistemic uncertainties, it's very, 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 very high. So I think I'm on time. Yeah, maybe, or I'm a little bit late, but I'm just finished. This is the second last slide. Some lesson learned from this exercise. So the comparison between principal faulting and secondary faulting exercise demonstrate the importance of accurate source characterization in PFDHA implementation. And for MPP site, the fault capability in the vicinity need to be carefully assessed, even if there are minor faults. So this means that the geology of the area is very, very important. As I show you with the last plot, also the source characterization, but we can do a good source characterization when we know very well the geology of the area. Again, let's take a study show a wide range of epistemic uncertainty, and this is mainly due to the difficulty in the characterization of the seismic source. And when we are working on a low seismicity area, major efforts are expected in source characterization to reduce the epistemic uncertainties. The predicted displacement vector varies between model. I already told you during the talk, and this may be critical for different engineering application because some installation could be more sensitive to the lateral displacement or to the vertical displacement or to the net displacement. So this is very, very important also in the application of this model. Practitioners of PFDHA needs to consider the tectonic environment of the area. This is now obvious, but this was not obvious during the first step. Style of faulting matters. It's very important to choose the appropriate model for the appropriate area in order to avoid very large errors. And yes. The complexity of the PFDHA models need a detailed hazard input document that clearly describe all assumptions made to avoid any misinterpretation. For example, if we take Young's paper, it's very well written, everything is explained, there are all equations, all coefficients. But if I build my code following Young's 2003 and maybe Paolo build his own code, at the end we will have two different hazard curve. Maybe not be the difference are, if we do a good job, the difference are very low, but we still have a difference in the hazard curve because at the end all assumptions are not written, but not only in Young's paper, in any PFDHA paper published so far. And these findings are useful not only for critical nuclear installation, but also for other critical infrastructure such as dams, bridge, pipeline, and so on. So just to conclude the talk, and maybe start some discussion if we have time, in my honest opinion, few things that are very important nowadays in PFDHA. So the first, I would say, never stop collecting data. For PFDHA, the data is it's like oxygen, and because now we have two databases, they are very good, Sure and FDHA database, but it's not enough. We need to have more database with more data, and so never stop collecting data. Maybe this is a message for geological for geologists, earthquake geologists. Then geological study always before a PFDHA analysis. Better later than never, okay, but before is better, is much better, because as I show you, the difference that can we have in the PFDHA hazard curve when the geological parameters are very poor constrained. And then I hope also that PFDHA will grow a lot in the next years. What I mean with this sentence, when I think PFDHA can be considered the maybe the son of PSHA, or the PSHA is the grandfather of PFDHA, but PSHA now is very well established everywhere in the world. Okay, PSHA was born at the end of '60 with the work of the paper of Cornell, Esteva, McGuire, and then grow a lot during the 18th and the 19th with a massive application in the nuclear installation in the United States, with also with the shock protocol has been taught during those years. And so now PSHA is very well established, and PFDHA, no, it's not very well established. I think there is no country in the world that has some regulation for PFDHA. Sometime when you show the the hazard curve to the regulators, it's difficult to explain that numbers, what that number could mean for a critical infrastructure. But I think PFDHA is younger than PFDHA, but now we have a lot of tools. We have machine learning, we have physics-based modeling. We also have this non-ergodic approach for ground motion models. So we have a lot of tools that in the 16, 19, 18 were not available. And so for this reason, I think PFDHA in the next maybe 10 years will be at the same level of PFDHA. And so this could be a good for us, because maybe we have more work to do. And then the tech talk will be published, I hope, in the next year, on the first half of the next year, and you can find everything in that document. So thank you very much, and yeah, time for some question if there is any time.
So thank you, Alessandro, for the very interesting talk. And if there are any questions from the audience, you can unmute or put on the chat, whatever you want. Okay, if everyone is shy, I will start. So I would like to ask you, in your opinion, where a practitioner should put more effort. So in the site characterization, or in choosing the right model, or so which step is the more critical?
Yeah, good question. As I said, there is no always compared to PFDHA. Now PFDHA, for example, for let's say for a nuclear acceleration, there is the shock protocol. So it's very, very established. You know what have to do for seismic source characterization, for ground motion modeling, and so on. So where the practitioner has to put more efforts, it's I think everywhere, but maybe in the characterization of the site, because if before to start a PFDHA analysis, the practitioner know very well the site. I mean, they know the geology, they know the geometry of the site, the kinematic, the slip rate are very well constrained. I think in this way they are going to reduce the epistemic uncertainties. And then for PFDHA, they don't have too much choice. I mean, if they are in the normal faulting environment, they can choose between Young's and maybe Vicini and stop. So a practitioner maybe they don't. A practitioner not has the tool to implement a PFDHA model. So sometimes they use the already published models, but they have a tool to do a very good geological study before to start PFDHA. So I think practitioner can put more efforts in this aspect before to start PFDHA, because you are going to reduce epistemic uncertainties then.
Yeah,
but there is work for everyone. I mean, there is work for practitioner, there is work for researcher, there is work for regulatory bodies. So also we need some guideline in application of PFDHA. So I think there is work for everyone.
Okay, is there someone else who wants to ask? Okay, Paolo.
Thank you, Alessandro. Really, I think it's very important to the group having this talk in the YouTube, because it's dense of information and needs to be maybe rewatched to see the interesting comparison. So we have the opportunities to discuss, you and me, often, but I would like to it's a question, it's a comment, I don't know, ask you this question here in the group because can be of interest also for other people. It is a question arising from one bullet point at the end, that is geology first, but also from one of the very first slides at the beginning. So for IAEA, PFDHA is recommended, no, in two cases.
Yeah.
When you have the principal fault, maybe the next one. Okay. If you have a principal fault in the site vicinity or a secondary in site area and or secondary in a site vicinity, okay? But okay, if you have an earthquake, okay, you know maybe what is principal and what is secondary. But this is for a capable fault before the earthquake.
Yeah.
So you have to decide before what is principal and what is secondary. It's not so straightforward. But in your experience at IAEA, is there any indication for state members on what on which geologic information you have to know to define if one fault is primary, principal, and what is secondary? Maybe is you know, stupid question, but I think it's not so easy, right, to define before.
No, it's not easy. As far as I know, there are in the IAEA, there are some indication to say if a fault is capable or not.
Yes.
There are some paragraphs that help member states to decide if a fault is capable or not, but there are no indication, if I remember well, about the primary and secondary faulting. And I think also in this case, a geological survey is very, very important during the installation of the nuclear, maybe also before the installation of the nuclear site.
So this is in charge of the investigator.
Yeah, this is in charge of the in the preliminary phase of the installation of the nuclear facility. Maybe it's a phase that it's maybe 3-5 years long, because you have to acquire all information about the geology, seismological information, and so on. You have to install also some station, and you also have to collect all the data, not only for the fault in the site vicinity, but also in area larger. So I think before to install the nuclear installation, you must be sure that the fault that you find or not in the site area is primary or secondary. So it's not something that you can say just with 1 or 2 written rules. So you need a geological survey to say this. You have to prove this, and then the regulatory body will read your report, and if they are convinced by you, they will accept your decision, and then maybe you can go ahead with installation of the nuclear facility.
Okay, thank you.
Okay, is there okay, someone Oshan. Oh, sorry if I mispronounced your name, but well, you can ask your question.
Oh, hello. I'm Osang Kwon in Korea, and last week I met Alessandro and Paolo in IAEA workshop. So thank you for inviting me in this presentation. I have a similar question with Paolo. As you know, in Korea, we are in the very, very, very low seismicity region. So maybe our result will be same as the retail earthquake as you studied. So I have a question about the how can we make a definition about the primary fault and the distributed rupture. So last week, Paulo was give the presentation about the definition of the primary fault and the distributed rupture. But if we adopt that definition in Korea, like as a low seismicity region, it is very difficult to give some assessment. So we are now thinking about how we adopt this method in Korea tectonic setting. So my key question is can we adopt the definition of a primary fault and distributed rupture in Korean tectonic setting? Can you adopt this definition?
Yeah, I think so. Maybe Paolo you have an answer, better answer than me, but of course you can adopt this definition also in low seismicity area. Because there are two different things, the primary fault and distributed rupture. Distributed are something linked with the principal fault, and for the principal we have you should have an evidence of the fault plane or also before the earthquake. So when you are doing your geological survey, you should find where is the location of the principal fault. For distributed, sometimes no, you can have you can map some distributed ruptures when we had some cases, as Paolo shown last week. Some primary distributed rupture, they are very, very large and can be also mapped before the earthquake. But I think you can apply this definition everywhere in the world. Paolo, I think you agree on this?
Yes, for sure. Yes. In fact, my question was about the issue of classifying a rupture before the earthquake in terms of primary or second. You can, if you can map before, it means you have a fault. You have at least a pre-existing fault. But sometimes distributed ruptures manifest in places where you have no pre-earthquake evidence. So that's, you have to consider this, and you don't know before. So this is one case. Or you can have a pre-existing fault that can be secondary or primary, but you need the primary fault, in my opinion. In any case, you need the main one, and then
let's say
the secondary one.
Let's say a very extreme case. I am a consultant, and I really have no idea if the fault is primary or distributed. But this is a very extreme case. I can apply both model and weight them in a logic tree. I can also do this. Otherwise, there are no guidelines, so there is no one that can tell me this is wrong. So I can do also this, but this is a very extreme case. When I have maybe I have a 5 kilometer fault, but I am not sure if this a principal or a distributed fault. And I can also apply both methods. Let's say in Korea, it's a strike slip environment, right?
Yeah, strike slip. And
so I can apply, for example, I can apply Petersen model or Takao, let's say Petersen. And the one branch of the logic tree with the primary empirical regression, and the other branch, the one for the distributed. This is a very extreme case. But yeah, we need again linked with a question made by Francesca. We need also regulation from regulators. We need everything in PFDHA. So these are very good questions. So Paolo said the stupid question or obvious question, but it's I think practitioner and consultant are facing these things very, very often, and in the future more often.
Okay, thank you.
Okay, I think Francesco raised his hand.
Hi, sorry about that. So just as a follow-up and on this discussion about primary and distributed, then in this epistemic error, then you will include also the discretion of the geologist then, because if deciding whether it's the primary or distributed, then it's something that's when it's not clear, you know, at some point you have to, I don't know, decide, I guess.
If you have this, but this is it's a decision for the PFDHA models not in the geology of the area. So it's not an epistemic uncertainties of the site. So it's an epistemic uncertainties of the models that you can apply for principal and distributed.
Okay.
So you don't have a probability surface rupture for a principal fault or for a distributed fault. So you have, but they are two different things. So two different equations.
Okay.
So it's not so straightforward the comparison. So yeah.
Yeah, that's what's striking me a little bit, you know.
The epistemic uncertainties that I'll show you in one of my last slides, taking account the moment magnitude of the source, the occurrence rate, and maybe I can show you because I put some slide at the end just for some question about this. Let me share again the screen. So this is, for example, the logic tree for the source characterization for the Kumamoto. We couldn't do any geological survey during the project, so we just took the information from the literature. Japan is a high seismic area, so the faults are very well known, are mapped. There are also database very well done, and so we did this logic tree for the source characterization in Kumamoto. Epistemic uncertainties in the magnitude, mmx and the mmx plus or minus 0.2. The epistemic uncertainties in the earthquake occurrence rate and also in the fault source. So combination of one segment, two segment, three segment, and so on. And this is the logic tree for the Letei. Low seismicity area. There is no data before the earthquake. The full database, there is a full database, but it's very poor on information for this application. There is a huge uncertainties in the seismogenic thickness. The earthquake was 2 kilometers depth. The geological studies say 4 kilometers, could be also 10 kilometers. The magnitude range from 4.9 to 6 point something, and don't remember, so a big range, and also the slip rate. And so you see the difference here when we don't know nothing about the source characterization. But the epistemic uncertainties that I show you here in the last slide is only about the epistemic uncertainties in the source characterization. If you have also the uncertainties in the primary and distributed, I mean, if you carry out a very good geological survey, you must don't have these kind of uncertainties. But if you have also these uncertainties, so maybe at the end you could have a very a very large 90 confidence interval boundary. So yeah.
Okay, thank you. And thanks for all this information. As Paolo said, it's important. It's on YouTube because I have to catch up a lot on what you said.
Yeah, I put the shirt only for the YouTube. I know that.
Yeah, thank you. You shaved as well.
On YouTube, yeah. I also shaved. Yeah, right.
Thank you.
You're welcome.
Okay, Franz.
Okay.
Ti sentono?
Can you hear me?
Yes.
Yes, it's a magic because we are in the same room. So I'm using the Francesca microphone actually. So thanks. I again come back to the distributed versus primary rupture, I know. But I was just wondering now, imagine, for example, a strike slip fault and our site is just on the tip, lateral tip of the fault, where maybe there is a lot of distributed deformation, distributed faults, something like a horse tail, I don't know. And so I'm wondering, should I choose primary or distributed equations? Because it may be in that sector we don't have a clear footprint of the principal fault. So I don't know if there is a kind of, I haven't done this calculation ever. I don't know, maybe you have done, but is there a big jump in the probabilities in the curves as you jump from primary to distributed, even if the distance is close or not?
Yeah, it could be. Yeah, let me share again. Sorry. Yeah, maybe I don't have to stop the sharing. So yeah, it could be a big jump because for example, if you are on the tip, maybe you are not 5 kilometers far from the principal fault. Maybe you are here in the first meters, or in a distance less than let's say maybe 200 meters. So maybe you can have a probability of distributed surface rupture, that is the probability that shift your hazard curve in the y-axis. And I have to do some calculation to tell you if this step is big or not, but maybe it could be in the order of 10 or something like that. Maybe you can have for the principal, let's say 10 to minus 6, and for distributed something maybe between 10 to minus 7 or 10 to minus 6. So maybe, yeah, the difference, if you are on the tip and if you are very close, the difference are not so much higher if you are if you are 1 kilometer or also 500 kilometers, this difference become to be much larger. But you need I mean, if you need this in your study, you need to call a very good earthquake geologist, maybe.
Okay, I think there is Paolo. Who
Yes,
is
just to
next.
say that I liked very much the question by Franz, because in fact the difference, I don't know, it could be a nice exercise that suggested by Franz. And but if you don't have geologic evidence of a distributed there, one can avoid the analysis, because maybe it's just outside the area of where investigation is required. So I liked very much this question. I think it's an interesting point. The difference just very close to the principal.
Yes.
Yeah. Okay. Sorry.
Okay, so I think we can kind of close. I want to thank again Alessandro for the really interesting talk.
Thank you.
And yeah, it will be hopefully soon on YouTube if everything goes right. And if someone else wants to be the next speaker, just send an email to me, Paolo, or Stefan, and we are hoping to continue this kind of meetings, which I think it's quite useful.
Okay, thank you for the invitation, and see you around. Thank you. Bye.
Thank you. Bye. Bye-bye.
Ciao. Ciao, ciao, bye.
Ciao.